Hi everyone, welcome back again. So in the last lecture we have started discussing about network measures, and we have discussed cases where we have seen different use cases where network measures plays an important role. Particularly I think we stopped at discussing the degree of a node, right? So the degree of a node is a very important property, and today we will discuss how we can use it for further defining other kind of metrics. So one such property is degree distribution, right? So what is degree distribution? So as the name suggests, we basically draw the distribution of degrees of nodes. And when it comes to distribution, I hope you are aware of probability distribution. There are two kinds of variables. One is discrete random variable, other is continuous random variable, right? So in discrete random variables, we basically relate to quantities like probability mass function. In continuous random variable, we can relate it to probability density function, right? So if you do not have ideas about these measures, right, I strongly suggest you guys to look at fundamentals of probabilities, right? So we will get ideas about this. Okay, so degree is essentially a discrete variable, discrete quantity, because we can't say that the degree is 2.553, right? A degree can be 1 or 2 or 3 or 4 and so on, right? Degree is always an integer, right? Positive integer, in fact. Okay, so degree distribution of a network is the probability distribution of the degrees of nodes over the whole network. Okay, first I will quantify what is degree distribution, then I will give you an example, and then I will tell you why this is so, this is such an important metric. Okay, so let's take a graph G, V comma E. V is a set of nodes and E is a set of edges, where the number of nodes is n, okay, capital N, and let us denote Pk, okay, P sub k, Pk as the probability that a randomly chosen node has degree k. Okay, so this Pk is important. So basically it is saying that, so Pk is that degree is small k, right? So Pk, I mean, you can write it in another way. You can basically say that Pk is Pk equals to small k. So this is the random variable, capital K, and small k is one value of the random variable, right? In our case, this random variable can take, say, 0, 1, 2, 3 and so on and so forth. So degree can be 0, degree can be 1, 2, 3, so on. Degree can also be 0, by the way, remember this. For example, if a node is disconnected, right, if the node doesn't have any edges, right, incident on that particular node, so the degree can also be 0. Okay, so how do we define Pk? So P sub k is basically a fraction of n sub k and n. What is n sub k? N sub k is the number of nodes of degree k, right? And what is n? N is the total number of nodes. So you are basically asking that how many number of nodes are there whose degree is k, right? And you basically divide it by the total number of nodes, right? That will give you Pk. Okay, so you can actually define P1, P2, P3 and so on. So P1 would be N1 by N, P2 would be N2 by N, right? P3 would be N3 by N. What is N1? N1 is the number of nodes with degree 1, N2 number of nodes with degree 2 and so on and so forth, right? So this Kpk, right, in our case 1 P1, 1 comma P1, right, 2 comma P2. Now, these are standard notations, by the way, right. If you are not familiar with these notations, please go back and read the basics of probability. 3 comma P3, right. So, this represents the degree distribution of a particular graph. Okay. So, of course, if you know, these are different quantities, what's the mean degree? So, the mean degree would be summation of kpk, right, where k ranges for whatever 0 to infinity, right. Yeah, of course, infinite number of degree, that's not possible, but you basically go up till, you know, whatever the maximum degree that is possible. You can say that 0 to, right, it can be k max, for example. Okay, and that would give you the average degree or the mean degree of the graph. Okay, mean degree of node in a graph. Okay. Now, why this is so important? Let's look at first. Let's look at an example, and then we discuss. So let's take this G1. Okay, this is a graph, and how many nodes are there? We have 5 nodes, so n equals to 5, right? And let's look at what are the degrees present in this graph. So we see that, you know, what's the max degree? What's k max? Okay, k max is, look at this one. This is 3, right? 4, right? 3 and 2, right? So max degree is 4. Okay, so we will actually take 1 P1, right? We'll measure 2 P2, 3 P3, and 4 P4. Okay, so in order to measure P1, what I need N1 by N. What is N1? Number of nodes with degree 1, right? How many nodes are there in this graph with degree 1? 0. There is no node with degree 1, right? So this is 0 by 5. What is P2? P2 is N2 by N. How many nodes are there with degree 2? This one and this one. So there are 2 nodes. So this would be 2 by 5, right? What is P3? N3 by N. So how many nodes are there with degree 3? We have 1 here and 1 here. So this would be 2 by 5. What is P4? P4 would be N4 by N. How many nodes are there with degree 4? There is only 1 node with degree 4, right? So 1 by 5. Now you can also cross check it whether you have missed out some nodes. So you can actually sum the numerators of all these fractions. So 0 plus 2 plus 2 plus 1. So this would be 5. So we check whether 5 nodes are there in this particular graph or not. There are 5 nodes, so it's okay. Okay. So once we get this quantity, so then P1 is 0, P2 is 2 by 5, right, 0.4, right, P3 is also 0.4, and P4 is 0.2. Okay. So then we can easily plot this. So as you see here, this is the distribution, so discrete distribution. So you have 0, 1, 2, 3 and 4. So there is nothing corresponding to 0. There is 0.4, right? So let's say this is 0.4. So this is bar graph, right? So this is 0.4, right? This is also 0.4, right? Right, in one, sorry, this is essentially 0, sorry. So this is 0, right, because P1 is 0, right? This is 0, this is 0, this is 0.4, this is 0.4, and this is 0.2. Okay. So it also satisfies the probability mass function, you know, constraints, which basically says that, you know, all these PIs, right, PKs in our case, should be greater than or equals to 0, and sum of PKs, right, should be 1. You see here 0.4 plus 0.4 plus 0.2, this is 1. Okay. So therefore this is a distribution, right, probability mass function. Okay. So now this is discrete, right? Now it may happen that, you know, there is no node with degree 5, but there is again one node with degree 6, right. So corresponding to 5, x axis at 5, the value would be 0, y would be 0. Again corresponding to say 6, you have some values, right. So you see that at certain points you do not have any values. So this is kind of a discrete in that sense, okay. So what we generally do, discrete distribution, right, if you look at pictorially also, this is difficult to compare. For example, you have two discrete distributions, you can compare, but visually it would be difficult to compare. So what we do, we basically convert it to a continuous function, where instead of looking at the the probability mass function or probabilities at every k, we basically measure something called cumulative degree distribution. So again, this is a very standard term in the probability. This is called CDD, right? Cumulative degree distribution. What is this? So cumulative degree distribution is given by the fraction of nodes with degree smaller than k. Okay. So Ck is in k dash by k, right, as you see here, right, where k is less than equals to k, where k dash is less than equals to k. What does it mean? Say C3, right. So C3 would be n1 plus n2 plus n3 divided by n, right. So these are the nodes whose degree is less than equals to 3. Okay. This is cumulative degree distribution. So why this is useful? We will take an example, we will see. Similarly, the complementary of that CDD is something called CCDD, right, complementary cumulative degree distribution. So this is essentially 1 minus Ck, meaning that is the fraction of nodes with degree greater than or equals to k. Now if we take equals to here, then it would be only greater than k. If we do not take if we do not take equals to here, then it would be greater than equals to k. So you can adjust it, right. I hope you understand. So this complementary cumulative degree distribution CCK is 1 minus Ck, which is basically say let us say CC4, this would be, and say there are max n6, right, there are nodes, max degree of a node is 6. So it would be, if we take greater than equals to, then it would be n4 plus n5 plus n6 by n. Okay. So you see that this is just a complementary of this one, right. Now why this is important? Now let us take an example. Okay, let us take this graph, right. We have already seen this one, and n is 5, n1 0, n2 2, n3 2, n4 1. Therefore you have seen p1 is 0, right, p2 is 0.4, p3 0.4 and p4 0.2, right. So cumulative degree distribution, right, CDD. So C1 would be 0, right, C2 would be this plus this, which is 0.4, C3 would be this plus this, I mean P3 plus P2 plus P1, which is 0.8, and C4 would be 0.2, I mean P4 plus P3 plus P2 plus P1. Of course this would be 1. Okay. Similarly, cumulative, I mean the complementary one would be 1 minus C1, which is 1 minus 0, 1 minus 0.4, 0.6, 1 minus 0.8, 0.2, 1 minus 1, 0. Okay. So if you plot this one, you see that in case of CDD, it is growing, right, from 0 to 1, right. So for this graph, the CDD would look like this. This is 1. Okay. Of course, then if this curve looks like this, then the complementary one would be the mirror image of this one, right. So it starts from 1 and it would stop at 0. So this would look like this, exactly the mirror image of the other one. And this is continuous. Why this is continuous? Because let us say you do not have, say you have some values p1, some value, right. Say let us say p1 is 0, p2 is 0.2, P3 is 0, right? P4 is 0.4 and P5 is 0.4, okay, something like this. So you see that if you plot it as a simple mass function, you will see that there is a 0, right? Then if you take cumulative redistribution, then C1 would be 0, C2 would be 0.2, this plus this, right? C3 would be again 0.2, 0 plus 0.2 plus 0, C4 would be, right, 0.6 and C5 would be 1. So there will be no, no break, right, in between. So you will see that it would look like this, 0, then 0.2, right, 0.2, 0.2, 0.6 and 1, something like this, okay. You will see a plateau here, I mean as a horizontal line here. Similarly CCTT, okay. So now this function, right, the degree distribution, if you plot degree distribution, right, say you have graph, you have a huge graph and you plot the degree distribution, so this is k and this is pk, right, and you see some points, right, like this. At every k you have a pk. I mean, of course, this it would not look like this, right? It would essentially look like this, right? Like this. So you will have point like this, right? Something like this. Okay, for every k you have a point. Now, if you take real networks, biological network, social network, doesn't matter, you will see that it follows a particular property which is called power law. What is power law? Power law is a particular function. For example, we have logarithmic function, we have heard about logarithmic function, we have heard about linear function, for example. Power law is also another type of function, right? A power law is a functional relationship between two quantities. We have two quantities x and y, right? And power law indicates a particular relation between x and y, right? The relation is one quantity varies as the power of another, right? Say one quantity is x, another is y. So x will vary as the power of y. So the power meaning say x to the power beta, where beta is a constant, okay? This is called power law. Let's take a simple example of a power law. Let's take, area of a square. You have a square, right? And the length of every side is, let's say, L, right? So what's the area? Area of a square would be L square, right? You see that A varies with the power of L, okay? Now this is a power law. Now this power law has a nice property. Remember, I haven't connected the relationship between power law and degree distribution. Let's only focus on what is power law function. This is a power law function, okay? Now this has a nice property, okay? The property is, say you double the size, double the length of a side. So earlier it was L, now this is 2L. What would the impact on the area of area of the square, right? So it would be, so then the new area A dash would be 2L square, which would be 4L square, right? So 4 is a constant. So you see that this is proportional to A. A dash is proportional to A. Why? It is just a scale, it basically scales up the value. Earlier it was 1 time L square, now this is 4 time L square. But the functional form, right, that one is a power of another, that remains same, okay? This property is called scale invariant property. One attribute of a power law is that it is scale invariant, okay? Let's take a function which is not a power law. Let's take y equals to log of x. Okay. Now what you do, you double the value of x. Now this would be log of 2 times x. So this would be log 2 plus log x, right? If you think of it from a, you see that this is not scale invariant, because when you scale this thing up, right, the value of x, right, what happens is that you get a new quantity, but this is addition. This is not, it is not scaling up or scaling down log x. Now this is not proportional to y. Okay. So that's the beauty of power law. Now why this is important in this context? It turned out, so people analyzed lots of such social networks, right, biological networks also, and it turned out that the degree distribution, this pk, right, p sub k, it actually follows power law. Okay, something like this: fx is a to the power a times x to the power minus k, or minus gamma. It's basically minus gamma, right? You see that this is also power law, but here the power is negative. That is okay, right? In this case, the power was positive. Now this is power. This is negative, right? What it is saying, that pk would be a times k to the power minus some constant gamma. Okay, so it can also be written as a times 1 by k to the power gamma. What does it mean? It means that as k increases, right, so pk is now inversely proportional to k. As k increases, pk value will decrease. So as the degree increases, degree of a node increases, the fraction of nodes with that degree will decrease. Okay, so I mean why suddenly I got this formula? Now I suddenly got, I mean this is not something that came magically, right? Let's say, there are many such graphs which have been analyzed manually, right? Meaning that people essentially computed the degree, then plotted the degree distribution, and then fit the appropriate function which describes the distribution, right? For example, this is an example. So this is World Wide Web network, WWW network, okay? And this is directed graph. So therefore, we have both in degree and out degree, in degree distribution and out degree distribution. Let's say in degree distribution, okay? So this is k in degree of node, and this is pk in, the fraction of nodes with certain in degree. And you see these dots, right? So these dots are basically is p k in values at every pk, at every k in. Let's say k in is 5, and this is, and let's say this is k in equals to 5, and we have some values pk in. So these are dots. Now which particular function, right, which particular function best fits all these dots, right? So people have tried with multiple functions which can fit this one. You can take log, you can take exponent, right? Doesn't matter. And but how do you know that which function fits these data points properly, right? You can take the error between, let's say you have a function like this, okay, and then you basically see the distance from this point to this line. So this is the distance, this is the distance, right? You sum all the distances. These distances are basically errors, right? So the best fitting curve would look like this, right? Which would basically be kind of an overfitted curve. But if you think of standard probability distribution, right, say you take binomial distribution or Poisson distribution and so on and so forth, then you see that the best fitting curve would be power law curve. Okay, and the beauty about again this power law is that if you take log in both the sides, let's say the square, again the area of a square, right, say a equals to L square. If you take log of a would be 2 log of L, right. What is this? This is basically y equals to mx, right, y equals to mx. Y equals to mx is what? This is basically an equation of a line, right. Let's say this one, right, f of right, f of x, let's say this one, right, f of x is a into x to the power minus k, right. If we take log, so this is y equals to this one. So if you take log of y is log of a plus, right, minus of k log of x. What is this? This is y equals to mx plus c, where this is c, this is m, and this is x. So in the log scale, this power law looks like a curve, looks like a straight line. Okay. So this plot, you see that both x axis and y axis are in log scale, and if you fit a line, right, if you fit a line, you see that this line best fits all the data points. What is this green line indicating? This green line indicates the degree distribution, the best fit of a Poisson function. If you take a Poisson function, then it looks like this. Now you see that this is a worst fit, right? Of course, this is not the worst fit, but this is not as good as the power law, right? Because you see a lot of distance, lot of noise from the points. So many such networks similar to this World Wide Web network have been studied, and it turned out that the best fitting curve which best describes the power, the degree distribution is basically a power law distribution. Okay, and the beauty of this power law, I mean, I can take a whole lecture on what is power law, right? Say and what are the implications of power law. For example, you know, this power law essentially says that, I mean, if you do not plot it in a log scale, if you plot it in normal scale, it would actually look like this, a skewed distribution, right? KPK, right? What does it mean? It means that you have a lot of mass here and you have a very small, very few negligible mass here. What does it mean? It means that most of the nodes, say if you think of these points, right, these k's, so k could be 0, 1, 2, 3, but if you look at here, k could be say 100, 200, right, something like this. Basically says that most of the nodes in a graph have lesser degree, and there are very few nodes, right? There are very few nodes which have, you know, higher degree, right? You can also relate it to a social network. There are very few users who have a lot of followers. There are very few celebrities on social network, but there are a lot of users who are actually normal users like us, who do not have much followers, for example, who do not have many followers, who are not considered as celebrities, and so on and so forth. So this is power law, and if a network follows the power law degree distribution, you can blindly say that this network has a lot of nodes with you know, low degree, a small degree, and you have very few nodes with a lot of degrees, right? Now, this power law is also called as Pareto distribution. So if you look at you know, advanced probability theory, you may have heard about this Pareto distribution. It also says the same thing, right? In fact, the Pareto distribution or power law, you know, this kind of function appears everywhere, right? It basically, this concept was borrowed from social science, right, where, you know, it was said that, you know, 80% wealth of a society, you know, are with 20% of populations, right? and rest 20% of wealth is with 80% of population. This is also called 80-20 law. This 80-20 law is very famous in social science, right? It is also said that in another context that 80% profits are caused by 20% of employees in an industry, right? And rest 20% profits are caused by 80%. As 80-20 law is very famous. I will talk about power law, the interpretation of power law in the next chapter. We'll talk about, scale-free network, right, and other types of network models. We'll discuss more about this in the next chapter, right. So this is all about degree distribution. In the next part of this chapter, we will discuss other properties of a network. We look at centralities, we look at clustering coefficients and so on and so forth. So till then, stay with me. Thanks.